University Teaching and Learning Academy, ATAL popularly called. And the topic we chosen for this two-week FDP program, and that is architectural design for signal processing algorithms using approximation techniques. And this for this 2 week we have a number of very renowned resource persons. They already contributed significantly to particularly to this architectural design and in the signal processing area. And these are the this talk about this program will going to be started with Professor Pramod Kumar Meher. And I feel deep honor to introducing him because he is my supervisor and whatever I learned from him. So Professor Meher, he is a graduate he is a product of Sambalpur University. He did undergraduate, postgraduate and PhD from Sambalpur University from 1976, 1978 and 1996 respectively. He was a reader in electronics from Barampur University from during 1993 and 97, and a professor in computer applications in Utkal University during 1997 and 2000. He was a senior research, he holding senior research positions in School of Computer Engineering, Nanyang Technology, University Singapore during 2004 to 2016. Currently, he is a senior professor with C.V. Raman Global University, Bhubaneswar. He has contributed nearly 250 technical papers to various reputed journals, conference proceedings, which include 90 IEEE transaction papers. He has also co-authored a very popular book, that is Arithmetic Circuit and DSP applications. Widely people they referring this book. His current research interest includes signal processing, cyber security, intelligent computing, smart IoT applications, edge computing and analytics. He was a speaker in the distinguished lecture program of the IEEE Circuit and System from during 2011 to 2012. He has visited more than 20 countries for his research assignment and delivering invited talks. He is a well-known person in the field of architecture design and signal processing within and outside the country. He has research collaboration with faculty and research scholars of top technical institutions of India and abroad. He has received several recognition at national and international level. A few of them mentioned here. He has served as the associate editor, a very prestigious jobs for the IEEE transaction on circuit system for video technology, IEEE transaction on circuit system 2 express brief, IEEE transaction on circuit and system 1 regular papers, and IEEE transaction on very large scale integration and systems. Currently, he is serving as an associate editor of IEEE transaction on circuit system 1 regular papers and international journals of circuit, system and signal processing. He was a recipient of Samantha Chandrasekhar Award for excellence in research on engineering and technology in 1992. 1999. He has been a fellow of Institution of Electronics and Telecommunication Engineering, India. He is a senior member of IEEE since 2003. He was elected as a fellow of Institution of Electrical Engineers.
The hardware design programs in their and conduct several courses like this so that many students can get the necessary skill and expertise and the required basic knowledge, which is very much lacking nowadays in our universities and institutions. This subject hardware design is not given adequate emphasis. Very rarely in few institutions we find that this course is offered. Therefore, this FDP program definitely is quite important. On the other side, when this IoT is evolving and we need a lot of low-cost chips and high-performance chips at the user side, or what we call the edge of the network, IoT edge. If we look at cloud, maybe quite far, here to the edge of the local area network, we can have fog, and our IoT sensors will be connected to the edge devices. Therefore, it is very important to design low cost, low power chips which will process the data from the sensors for applications like video surveillance, smart video surveillance, and real-time alert system in healthcare applications, and data-intensive applications relating to the financial decisions. So this topic is important. And the other side, as we all know, that machine learning and deep learning particularly has become a something like technology known to common people. Nowadays, common man also knows that there is something like AI, something like machine intelligence, and know that deep learning is something very important. So, and the implementation of deep learning, now we need to implement through hardware accelerators, which will be specific chip, small chips, which will perform all deep learning applications. And there we have a lot of scope of approximate computing. Roughly, you may be guessing the meaning of approximate computing. Just like always, we do not need exact data. Now, suppose I am at Bhubaneswar, how far is Sambalpur? Then I will tell it is about 300 kilometers. That is important. Whether it is 303 kilometers or 305 kilometers, it is not important. Similarly, in signal processing applications and for deep learning applications, very often exact specification of a numerical value is only rarely required, not required very often. So if we do such computing devices where we need not bother about exact computing, we need something approximate value, the hardware will be very much simplified. The number of transistors used will be very much simplified, and it will be consuming very less power. So for IoT applications and for deep learning applications, this approximate computing has a significant role. And people already have been using this for quite some time for image processing and signal processing applications, and now all those will be utilized in machine learning and IoT applications. So this topic is very much timely. I will share my presentation now. As you know, the topic is mapping algorithms to architecture. Is it visible?
Yes, sir.
Yes, sir, visible.
Okay. So the slide is visible. So at first, we'll try to know what is an algorithm. Many of you know it. I will just refresh in the context of the hardware design. Then what do we mean by a VLSI architecture? Lot of different types of architecture we hear: software architecture, building architecture, and this word is very popular. But what is VLSI architecture? What do we mean by VLSI, and what is VLSI architecture? Then I will come to objectives of mapping an algorithm to VLSI architecture. Why we need, and how we do. How do we map an algorithm to appropriate architecture? This one I will show you by a story which we have learned in childhood. So, are you able to see the pointer? Whether the pointer is visible?
Yes, sir, it is visible.
Yes, sir.
Okay. Okay. So, here on the right side, there is a forest. And in the forest, there was a man living, and he had one pet wolf. Okay, and he was going to market to bring buy certain things. So market is on the other side of this small river. There is a small river, and on the other side of this river, left side, there is a market. So he had a small boat. In this boat, usually he and his pet fox, fox or wolf, whatever you say, they go to the other side, the river, very small boat, tiny boat. So with that tiny boat, they crossed the river and went to other side. Then purchased something like some fruits, vegetables, etc., and also purchased a goat. Then how they will cross this river? Because in the river, only the farmer and either the fox or wolf or the vegetables or the goat. Only one of these he can go with the boat. So he planned how safely he will move all the three entities: the vegetables, fruits, and the fox and the goat. So first of all, what he will do, he will take the goat to the other side. Okay. Then he will leave the goat on the other side and come back again to the market side. Then he will take the wolf and will take to the other side. Put the wolf to the other side, and he cannot leave the goat there. If you leave the goat there, then the wolf may kill the goat. So he will take the goat with him back to the market side. There he will leave the goat and take these vegetables and fruits with him on the boat, and he will cross the river. The fruits, vegetables, etc. he will put on the other side. It is safe. The fox will not eat vegetables. And now we take the goat again with him to the other side. So this is a sequence. It has to follow this way to move all these entities, the vegetable, the goat, and the fox, all safely. If you try some other way, then either the goat will eat the vegetable or the fox will eat the goat. So there was constraint here that this task is to be executed in this sequence. This is binding. Okay. So we can say this is an algorithm. The farmer had to follow this sequence of steps. So every algorithm is like that. Usually we will have a step-by-step procedure to solve a computational problem, how to compute something and or find out something by computing or execute some task. Generally, it refers to some computational task. So let us look at a simple algorithm. Find average of 4 numbers, x, y, u, and v. 4 numbers, you know it. Step 1, suppose I compute x plus y. Step 2, I compute u plus v. Step 3, then I add z plus w. That will be equal to x plus y plus u plus v. Then divide by 4. Okay, so I get the average value of x, y, u, and v. So a step-by-step procedure we are following. Here, of course, it is not unique. Some changes can be done. You can first in the step 1 you can compute w. In step 2 you can compute z. Okay. So in the context of doing or executing a computational task, it is a sequence of operations. Some computational operations required to be performed to complete the given task. Or you can say it is a sequence of arithmetic, logical, and data transfer operations to perform a given computational task. Okay, so how we do a computational problem, how we do a computation is impacted by certain constraint. In this problem, the algorithm that I told about the farmer taking the vegetables, fox, and the goat from the market to his home in the forest. So here the constraint was that the fox can eat or kill the goat, goat can eat the vegetables, so they cannot remain together. And there was a resource constraint. So this is the algorithmic constraint that how the kind of sequence he has to follow is constrained by the situation that the goat will eat something, the fox will eat something. Okay. The other is the resource constraint. The boat is small. Boat is tiny, small boat. So if this boat would have been bigger, then what would have been? With the tiny boat, it required to cross the river 8 times. With the tiny boat, the farmer had to cross the river 8 times. If suppose the boat would have been bigger, there would not have been, suppose, resource constraint. Suppose the boat can carry 2 entities. So what should have been the algorithm? The algorithm would have been different. The farmer would have perhaps brought the fox and the vegetables first to the forest side from the market, from left side to right side. Then he would have gone and brought the goat. So he would have crossed the river only 4 times, not 8 times. Suppose the boat would have been capable to carry all the 3, then he had just in one time he could have crossed the river. So this constraint came due to the limited resource. The boat was tiny. With bigger boat, the algorithm would have been different. So if he had to move faster, if he would not have enough time to repeatedly cross the river, he should buy a bigger boat so that at least he can come with vegetable and the fox at a time and some other thing another time, like that. In case of computational problem also, we have similar situations. When we need to do things faster, we have to have the computational resources which will facilitate faster computation. Similarly, other constraints could be there in computing systems. We will see in this lecture. I will try to be brief in some cases. So mainly 2 types of constraints we saw in the execution of the task. One is the resource constraint, the other is algorithmic constraint. In the example what I showed you, that the farmer crossing the river with all 3 entities he had algorithmic constraint that he cannot leave unattended the fox with goat and goat with vegetables. This is a kind of algorithmic constraint. So algorithm need to be such that all the 3 entities will remain safe. One will not kill other. And the resource constraint here was the boat was tiny. So 2 types of constraint we saw. And in computing system also similarly, availability and efficiency of the computing resources will be our resource constraint. And what is algorithmic constraint? Precedence behavior of the algorithm for scheduling the operation. What is the meaning of this? The meaning of this is what you need to compute first and what you compute subsequently, so that the sequence of steps is to be followed. Generally, this algorithmic constraint results from the data dependence. If the data is not available, you cannot compute. So, to facilitate the process of computing something, the input data need to be available first. That is a very basic and simple things. So the data dependence behavior sets the precedence. What should be computed first and what need to be computed next, subsequently. So in this example of averaging the numbers, we have like this. So you cannot change step 3 and step 2, you cannot interchange. you cannot interchange step 3 and step 4. Of course, step 1 and step 2 can be interchanged like that. Then the vital thing about computing is the time complexity of the algorithm. How much time it will take. How much time it will take again will depend on how the computation has to proceed. If, like our armor in the example, if we have limited resources, then it will take more time. Suppose we have a RISC processor. A RISC processor, most of you would have heard, reduced instruction set computer. So there, basically, this is a load store architecture. And for this, we will load X in register R1 first, load Y in register R2, then add the content of register R1 and R2 and store in register R3. So by this we compute Z. Z now is available at R3, register R3. Next what we do, load U. Now register R1 and R2, which were holding X and Y, are no longer needed. And we can load U in register R1, and we can load V in register R2, and then add the content of R1 and R2 and store in register R4. So already 6 instructions we have passed, and then content of R3 and R4 are added and stored in R1. Then content of R1 is divided by 4. That means dividing by 4 will be as good as do your left shift operation by 2-bit positions. Okay. Divide by 4 is easy. Or you can take a divider and do the division. All right. So to compute Z, 3 instructions. To compute W, another 3 instructions. Then your S is computed in another instructions and A is computed in another instruction. So total you required 8 instructions were executed by this processor. So that will take sufficient time because the memory access definitely takes very long time. Relating to other computations because data will come from main memory to the cache, maybe L1 cache, then L2 cache, and then the computation can happen only when the data arrives at the registers. But if you implement in a dedicated processor, means in the dedicated processors, we will be having adders, and suppose we have 3 adders. In this algorithm, we are doing 3 additions and we have 3 adders like this. So one adder is adding X with Y, another adder is adding U with V, and we get Z and W, which is added by another adder, the third adder, to give S, and there is a division circuit, divider circuit, or a shifter which will divide S by 4 to give the result. So this will be much faster. This will be very much faster because here you do not depend on the data for coming from the main memory to the cache to the registers and do the computations, and no need to transfer back any result to the registers or main memory. So this is much faster. It is known that generally such dedicated circuits for specific functions, this can be 1,000 times faster than what the other processors or what our computers do. And the power consumption will be just a small fraction of the power consumed by the computers. That is why these dedicated processors are of great demand in the context of deep learning implementation and also edge computing or IoT. Okay. So to implement any algorithm, we have choice of different platforms. One is the programmable processors. That is our whatever laptop or desktop computer, whatever we are using, or even the servers. Those are all programmable systems. They can perform any kind of computational task or run any kind of applications. For whatever computations you want, you just write a program and the compiler will be available in the computer, and that will generate the machine code which will be executed by the processor. So whatever computations you need to do, whatever applications you want to run, you can run by these programmable processors. And we have general purpose programmable processors. And also we have specialized programmable processors for different applications where our instruction set is so designed to cater to the kind of computations involved in that applications. Just like for image processing, video processing, signal processing, we have some specific type of computations always repeatedly performed. So for that, we have specialized programmable processors. Generally, it is called application-specific instruction set processors or ASIP. I'll give some examples. The data parallel processors, that SIMD machines are single instructions, multiple data stream. Single instruction stream, multiple data stream. So same instructions will be used for doing processing on different data, multiple data at a given time. So some computations like the addition of matrices or inner product computation and similar computations can be performed by such data parallel processors like SIMD machines or vector processors, where vector data can be given as input and vector can be obtained as output. And GPU also that kind of data parallel processor which is used for graphic processing, graphic programming unit. Apart from that, as I told, we can have dedicated processors which are realized by digital circuits consisting of adders, multipliers, registers, and for control operations, we may be using multiplexers, demultiplexers, encoders, decoders, shifters, counters, all these things we'll be using. And these dedicated, why they are called dedicated processors? Because they are dedicated to perform some specific type of computation. They will not do any other type of computations. It is just like a black box, give the input, get the output. So no change will be in that. But in dedicated processors also, there is scope for reconfigurability, or we can call a reconfigurable processor. The circuit could be modified to some extent, or just a new circuit could be generated to perform a different functions, altogether different functions. Those are FPGA, field programmable gate arrays. And the other is application specific integrated circuits. Generally, when we implement the dedicated processor in application specific integrated circuits, you cannot change it. Once it is fabricated, it will do the same job always. It cannot be used for doing any other job. And nowadays, the heterogeneous systems are coming up. That inside FPGA, you will be having some unit of programmable processors, and there are also some dedicated blocks can be there inside FPGA. Some hard-coded function will be there, so that could be implemented quite quickly. And that is a small ASIC-like unit will be there inside FPGA, or inside FPGA there could be a small processor, maybe an ARM processors or an Intel processor can be there in the FPGA itself. Okay, so we'll look at these briefly in the next slide. So this is what the design of a programmable processor. L1 case and registers will be there inside the processor or the primary case, and the secondary case can be outside L2 case. And they get data from maybe hard disk, data goes to main memory to L2 case, then to L1 case, and there could be I/O interrupts also, and the processing is done by the arithmetic logic unit available in the processor. So it takes a long route for having the input data and giving out the output data back, giving out the result to the main memory. So a lot of power consumption, often more than 90% of power is consumed by the data transfer from this main memory to the cache. And a lot of wastage of power is there. That is why these are power hungry processors. But they offer a lot of flexibility, support several high-level languages like our C, C++, Java, even you can run MATLAB and Python, and many high-level languages you can run in these systems. It has another benefit that relatively it will be cheaper, because these processors are produced in manufactured in large volume. Due to production in large volume, the initial cost or what we call non-recurring engineering cost, or the NRE cost, is much less in case of these programmable processors, general purpose processors. And generally it is a short time to market, because you can reuse some programs, in this case by small modifications of the program, which you can do quickly to have a different applications. But on this disadvantage side, it has very high power consumption. And if you really need to do the computation much quicker, then also it is not that fast like the dedicated systems what we had. And I was telling about ASIC, application specific instruction set processors. ASIC is also like a microprocessors. Just like in our desktop computers, we are having microprocessors. In ASIC also we have a microprocessor. But it is not having exactly same type of instruction set. The instruction set in ASIC will be different. Just like in signal processing, we need multiply, add operation. Or for image processing, often we need specific type of operations. So those operations, for those operations, we have specified instructions, specific instructions which can run in ASIC. So it is a specialized instruction set to accelerate the computation involved in signal processing and image processing or video processing applications. But on the other side, it has significant flexibility, like general purpose processors. Very well, it can do any applications like that is related to these different applications. And here the goal is to achieve better performance, higher performance compared to general purpose processors. And power consumption could be reduced to some extent because of the specialized instruction set. And the design cost will be also less. And because it is specialized, the area and the silicon cost could be low. And one SIP very often we use is digital signal processor. That is also called DSP. DSP is digital signal processing, and DSP is also digital signal processor. Digital signal processor is basically an SIP, and it has ability to perform repetitive multiply, accumulate operation, multiply and add. And bit reversal addressing, which is required in fast Fourier transform computation. It can do the loop execution also done here more efficiently. Then about FPGA, is there any requirement now that we give a break for 5 to 10 minutes?
Prabir? Hello.
We can give a break of maximum of 10 minutes.
Yes, sir. Yes, sir. Maybe 5 to 7 minutes, sir.
Yes, yes. Before 8 o'clock, everybody should be available.
Yeah, yeah. Okay. Okay, sir.
Okay. Whether the speed is okay or
Sir, it is okay, sir. Okay. And
okay.
ସେମାନେ ସବୁ ମ୍ୟୁଟ୍ କରିଦେ ଛାଡ଼
Sir, will you start?
Okay. So I was telling about PG. You can say it is analogous to the breadboard that you use for designing different analog circuits using transistors, resistors, capacitors, etc. Here in FPGA, we have two main types of resources. The configurable logic blocks are combinational units and having also registers, lookup tables, and it has muxes for control and registers also, and interconnects, which is programmable. You can see here that here the interconnections can be modified. So data can move in different directions. These are the configurable logic blocks where we can have different circuits, and the data from one part of the circuit or one CLB can move to other CLBs, and overall it can create a circuit for us. And specialized I/O blocks also it has. Nowadays, in PJ devices, we have got DSP blocks where we can do multiply accumulate operations, and hardware IP cores also we have, as well as processors, as I was stating. The other types, the heterogeneous multi-core systems, we can have different types of processing elements, and they can have data transfer from the main memory and to different types of can run different programs. And in the multi-core systems also you can connect with FPGA. A CPU can connect to FPGA and can run a heterogeneous system. And CPU GPU connection is very popular. Often we have in our desktop computers this through PCI Express. Generally, CPU interconnects the GPU. Lot of data intensive computations, parallel processing is done in GPU for basically for graphics. And nowadays, a lot of programs relating to machine learning, neural network, deep learning is also implemented in GPU. So overall, we can have heterogeneous systems that can have general purpose processor cores, as well as FPGA units, as well as GPU, and dedicated hardware logic also. So this is the very generic scenario in which we will have different types of processing systems altogether and can use it. Then, as you see, we have a large spectrum of the computing. Oh, we have scope for using different types of computing systems. So we need to look at for a given application and running given type of computation, what we should use. whether you will use FPGA or will use ASIC or FPGA with soft core and dedicated IP or multi-core system or simple general purpose processors. So it will depend on the different constraints that what is the speed performance required. If you need very high speed operation, upon you may have to go for dedicated processors, or you have to see whether your GPU CPU combination will be enough. And when you use GPU CPU combination, there the power consumption could be higher. If you have severe power consumption constant, then definitely you have to go for dedicated hardware or ASIC implementation. FPGA also consumes substantially high amount of power compared to the ASIC. So if power consumption is a concern, you have to go for dedicated hardware implementation, dedicated ASIC implementation. Then if the cost is the primary issue, right, and you have a large volume of production, definitely one has to go for the general purpose processors, where you can have possibility of implementing running an application with minimal cost. But you have to consume a lot of power for that. And that would be possible if you do not want very high speed computation. Then if you want to reuse the design, that means now you have a design and you want to have, you want to run another application, then your FPGA is good. Reuse design often will be facilitated by the programmable processors because you can store that as program. Reuse of system or subsystems is possible in most of the cases. If you have ASIC design, also you can use a subsystem in FPGA. Time to market versus design and development time. Design and development time in general purpose processors is generally less. So it is easier to do software programming because for dedicated hardware, there you can have possibility of lot of design reuse. But in dedicated hardware implementation, reuse is limited. Not that you cannot do reuse, you can do definitely certain things can be reused. But time to market is generally more in case of dedicated hardware implementation. We're talking a lot about dedicated hardware implementation, but that is going to happen through a VLSI architecture. So we need to understand what is VLSI and what we mean by VLSI architecture. Just a minute. Get the meaning of VLSI, I think this slide would be enough. That when the transistors were evolved, only single transistors and discrete components using transistors, several applications people were doing. Then few transistors were used to develop logic gates and the flip-flops. logic gates like AND gate, OR gate, NAND gate, and D flip-flop, JK flip-flops to have counters, etc. So, and multiplexers, counters, all these things were also done through medium scale integration, where 100 to 1000 transistors people used. Then in 70s, we had large scale integration using 100 to 20K transistors using random access memory and the microprocessors. And in the 80s, 81 to 1990, you can say that at the time of VLSI, 20K to 1 million transistors were used to have 16-bit to 32-bit microprocessors. And 1999 to 2000, it is called VLSI. But VLSI is a term which refers to all higher level also. VLSI, what you say, ultra large scale integration. 1 million to 10 million transistors for graphic microprocessors. And beyond 2000, the giant scale integration, more than 10 million or billion. Now we have billions of transistors. But generic way, ULSI, GSI all come under VLSI. People say it is VLSI. Generally, although this classification is there like ULSI or GSI, ultra large scale integration or giant scale integration, generally all come under VLSI. Generic way, people say it is VLSI. So, all this VLSI architecture, what is the basic building block? Basically, they will be doing computing, control, and storage. And most fundamental logic operations will be by the gates, NAND gate, NOR gate. They are more popular than XOR gate. So, and using the gates, the basic, most basic computing element is a half adder. Half adder is used to add 2 bits. Suppose A is a bit. Bit, you know, everybody, binary digit. That can be 1 or that can be 0. So A is a bit, which can be 1 or 0. B is a bit, which can be 1 or 0. You want to add. So what are the possible cases? Both the bits may be 0. A is 0, B is 0. In that case, the result is also 0. So we get the sum is 0 and carry is 0. So this circuit can give that when both are 0, then sum is 0 and carry is 0. When one of A and B is 1, one of the pair of input is 1, then your sum is 1, but carry is 0. That you can see from the circuit. When either of A and B is 1, then sum is 1 and the carry is 0. When both are 1, you can see that the result will be 1 plus 1 is 1, 0. Binary 1, 0. That means carry will be 1, sum will be 0. So you will have carry equal to 1, sum equal to 0. The transistor equivalent will be there. Basically, transistors, your NMOS, PMOS, or CMOS transistors could be used to have these XOR gates and gates, different types of gates, and half adder we can get using transistors. So transistors we can get half adders. And then you see we can use half adders to have a full adder. 1 bit full adder means what? It can add 3 bits. A is a bit, B is a bit, C is a bit. So A can be 1 or 0, B can be 1 or 0, C can be 1 or 0. And how much will be the result? All possible cases means all inputs are 0. All are 0 means here you see the carry 1 and sum 1 will be 0. This is 0 means here carry 2 and sum 2 also 0, 0 or 0 also will be 0. So result will be 0. When all are 0, then it will be 0. When only one of the three inputs is 1, then your sum will be 1 and carry will be 0. Only if only one we have got, then if either of A or B is 1, then your sum is 1, carry is 0, and C is 0. So in this case, sum 2 will be equal to sum, carry will be 0. So that's the case. Suppose if both A and B are 0 and C is 1, then here carry 1 0, sum 1 0, and here 0 and 1, sum 2 will be 1 and carry 0. Finally, you get carry equal to 0. If two of the three inputs are 1, if A and B both are 1, then your carry is 1, sum is 0, and here you see you have got C is also, if it is 0, that means you'll get 0 and 0, this is 0, this is 0, carry is 1, sum is 0. So if two are 1, then carry is 1, sum is 0. Similarly, if either of A or B is 1, then here you will have sum equal to 1, here we will have carry is 1, and here we will have carry equal to 1, sum equal to 0. So this is all you know, I am just telling you. So using a simple half adder which can be constituted from the transistors, you can add 2 bits, and using 2 half adders and 1 OR gate, you can have a full adder which can add 3 bits. And you can use full adders like this to do addition operations. So you have to add 2 4-bit words, 4-bit adder. So you take four full adders and pair a bit of the same weightage. You give to each of the full adders as LSB. You give A0 B0 to first one, A1 B1 to the second full adder, A2 B2 to the next full adder, A3 B3 to the next full adder, and the carry move forward, and you finally get the result 4-bit adders. So, and similarly, you can also have 8-bit adders using 8 full adders. And using adders, you can have multipliers. Suppose your A0, A1, A2, A3, B0, B1, B2, B3 are 2 words. You can multiply like this. So by bit AND operation, you get the partial products like this. Here in the circuit, B0 is having AND operation by the AND gates with A0, A1, A2, A3, and get one partial product. And similarly, B1 is ended with A0, A1, A2, A3, get another partial product, and add by the 4-bit adder for 4-bit multiplication like this. And similarly, you have other partial products and go on adding to the other. So you see, from gates, you are getting half adders. Using half adders, you can get full adder. Using full adder, you can have adder of different lengths, and using adders, you can have multipliers. But I'm showing is a very simplified way. That means the easiest way how from the transistors you build up different arithmetic circuits like adders and multipliers, and also you can have boxes like this. Boxes generally you use to select one of the pair of input. So here you have your suppose control bit is 0, then I0 will be available as output, and control bit is 1, I1 will be available as output. So it is a 2:1 box which can select one out of 2 input as output. Either I0 can be selected or I1 can be selected. Similarly, you can have 4:1 box select one of the 4. Either I0, if your control is 0, you select I0. If control is 01, select I1. If control is 10, you select I2. If control is 11, you select I3 as the output. So these are control circuits. Similarly, DMOX will do reverse. One input can be steered into different channel or different line, and can be used, the MOXes can be used as a barrel shifter to shift the word left or right to any number of bit positions. And also it has lot of use like design of LUTs and like lookup tables. MOX also used for the control operations. The other building blocks are the registers. I am telling you because these, unless you have revised the idea about these basic circuits, the rest of the things what you will encounter in the subsequent lectures might be difficult. So it is necessary to revise. A D flip-flop is a basic storage element which can store 1 bit, or it can be called as 1-bit register. So whatever input you have as at the point D, so D is an input bit. And generally when the clock rises, on rising edge of the clock, this input D will be available as output Q. That is, D goes to Q when clock is rising. Clock is generally a rectangular pulse. This is a rectangular pulse. When the rising edge of the clock, at that time, this input D will be available as output. So sometimes we have a right enabled signal. When right enabled signal is there, then only on rising edge of the clock, input can be available as output. When right enable is 0 means the flip-flop is disabled. At that time, the input will not go to the output. Okay. So if you take suppose 4 of the flip-flop I take, I can use it as a 4-bit register. That means to store 4 bits. Here in this diagram, D0, D1, D2, D3 are 4 bits. When write enable is 1, that is you have enabled writing, and the clock pulse goes high on rising edge of the clock. This D0, D1, D2 will be available as output Q0, Q1, Q2, Q3. D0, D1, D2, D3 will be available as output Q0, Q1, Q2, Q3. This is basically these registers will have another role in pipelining the circuit. That means it will divide the circuit into 2 halves. When one half is doing certain job, the other half will be doing some other job that I will show. So basically, the 4-bit register, suppose write enable is high and write data is available 1001. Then output when clock pulse goes high on rising edge of the clock, this will be stored, and it will be available as output when the clock is rising. So it is something like this. This goes, and on rising edge, this will be available as output. And these simple things can be used for different signal processing applications like implementation of FIR filters, complex multiplications, your FFT, everywhere you can use these adders, multipliers, etc. The equation what you see here is N-type FIR filter. FIR stands for finite impulse response. Here H0, H1, H2, H3, H4, Hn minus 1, all these are impulse response. Okay. And here Xn is the input, and Z inverse is the operation, is the delay operations. So if here Xn you have got, here you will have Xn minus 1. N is the current instant of time. Xn minus 1 will be the past instant of time. So here you will have Xn minus 1. Here you will have Xn minus 2. So this is the previous signal, previous to Xn minus 1. Similarly, here we will have old signal X n minus small n minus n plus 1. So basically, what you are implementing this thing in the FIR filter, you multiply the impulse response with the current input of signal and the past input signals, and uh, the product values of impulse response and the signal values are added together. Okay. So here we have like this. Here, if it is Xn is input, here we have a register. Here D is a register. On rising edge of the clock, Xn will be available here. Here Xn minus 1, Xn minus 1 will be available here. Here Xn will be available here. Here X, when Xn plus 2 is available here, at that time Xn minus 1 will be available here, and Xn will be available here, like that. And so all these signal values are multiplied by different multipliers and they are added. So this is a direct implementation of FIR filter in a dedicated hardware. This can be an architecture. This is a very straightforward architecture for implementation of FIR filter. This architecture you can have it kind of optimization where multiplications you can implement using approximate multipliers. Multiplication you can use you can implement using distributed arithmetic. Sometimes that gives very nice result also. You can use distributed arithmetic, so lookup tables could be used. And instead of multipliers, you can just do additions with lower complexity. That is possible. And you can use multiple constant multiplications method, single constant multiplication methods, because when you are multiplying with a constant, you need not to generate all partial products. You can have very less number of partial products, and your computation could be faster with less hardware, less power consumption. So different methods are there. This lecture will not be adequate to tell about all those methods. Subsequently, we have many learned experts who will be giving subsequent lectures. They will be able to tell you how to do all these things. There is immense scope to use approximate arithmetic here for reducing the complexity of multiplications. And because you generally do not need highly accurate computation. Generally, if you have got, if you multiply to 8-bit numbers, you will generate a 16-bit number. And it is not necessary to have all those 16 bits. You can have less number of bits. Still, you will have adequate accuracy that your whatever result you will get, that could be used satisfactorily for the applications. Okay. So in a simple way, for four-step filter, I had a diagram like this. When weights are constant, you have scope of implementing in a much simplified way distributed arithmetic approach, multiple constant approach, canonical sign digit approach, your single constant multiplication approach. Many different methods are there, and where approximation still could be applied. Okay, so when we talk about algorithms to architecture, or mapping algorithms to architecture, how do we proceed? For a given application to run, we have to compute several mathematical functions, several mathematical operations we need to do. Suppose one of the operations is fast Fourier transform. The equation what you see here is basically doing the fast Fourier transform. It is a brute force approach, the simplest way of representation. There are many fast algorithms, of course, are there to reduce the number of operations. If you compute like this, you will require n square complex multiplications. If your xn is complex, here e to the power minus j 2 pi kn over n. This is a complex number, and one complex multiplication will be there to get one product done. And here for each value of xk, you have n computations, and generally this equation requires n square multiplications. And there is the famous Politiki algorithm, which is proposed in 1965, that transformed the signal processing to be so popular. That requires n log n computations, and we have also done some work how when your input is real value, how we can simplify the computation, and the computational complexity could be reduced in that case. Anyway, so this is a mathematical expression which can be computed by efficient sequence of operations, efficient algorithm. And that algorithm you can write as a program, write as a C code, and run in a desktop computer. Okay, so that will be your general purpose processors to do the run the program. Instead, also you can have map the algorithm to a dedicated architecture, and the dedicated architecture will have a look like this: component 1, component 2, component 3, component n. Different components will be there. They are interconnected components. Different components are connected together, and there will be some control sometimes might be required. So different components will be given different inputs, and the output of some component also can be given as input to other components. So communication will take place from one component to other components, and there could be control, some control signal which will direct which output from which component will go to which other component. So basically the architecture consists of some functional units, dedicated circuits, which may contain adders, multipliers, and registers, something like that. And communication can happen from one component to other components as and when necessary. And there could be some memory units to store the data, and interconnections to facilitate such transfer of data from one component to other component, and control signals as and when necessary. So you can visualize dedicated architectures in generic sense like that. It can have several different components, where each component will have maybe registers, adders, multipliers, something like that, and doing some kind of function or a part of the function. and some storage registers will act as storage there, and then when necessary, and interconnect signals will be there for data transfer from one component to other component, and control signals will facilitate the appropriate direction of data transfer. Whether the speed is okay or any is it okay? So we have a computation suppose like this. While y is less than equal to 2, do this, y is transferred to a, then do the computation f equal to e times a minus e times b. Then next, g equal to a times c minus b times c plus d, and y equal to f times g. This we need to compute. So the first thing here is, here you are having two multiplications for f equal to e times a minus e times b. So simple, in the high school we know how to take some variable as a common. So it is e times a minus b and g equal to a minus b times c plus d. So it is a algebraic simplification. So we did an algebraic simplification to reduce the number of computations, which we are used to do. There could be many different tricky algebraic simplifications, trigonometric simplifications. All those things can happen. Then we can represent in a graphical manner. Graphically, we represent. So here your y is equal to a, and a minus b is done by here by one subtractor. Then e is multiplied with the result of subtraction. That is a minus b is multiplied by e, and a minus b is also multiplied by c and added with d, and finally the result of addition of d, which generates g, and on this side result of multiplication generates f. They are multiplied together to get y. So this computation is now graphically represented by this one. This you can say is a graph where the subtractor, multipliers, etc. are the nodes of the graph. They are the nodes of the graph. So here we represent this to a graph form. Mathematics is now transformed to the graph. Then how we map to the dedicated architecture depends on how much resource we have. If we have one subtractor, three multipliers, and one adder, then directly no change to this graph. This graph can directly lead to the architecture. But suppose you have a limitation of resources. If you can afford only one multiplier and one adder, then how this is to be implemented? That we may. So there the algorithm need to be changed to suit the architecture, or if you want the algorithm to be specific to improve the speed, then the architecture needs to be modified. You may facilitate more resources for implementing the algorithm if you want faster operation. So while doing mapping algorithm to dedicated architecture, the first thing what we do is a behavioral specification of the algorithm. What is behavioral specification? So that could be a pseudocode. which you can write in a procedural or any functional language. Then the algebraic optimization. What we did here, the algebraic optimization, and there you can utilize the trigonometric symmetries. What we do very often in the FFT simplification of FFT, reducing the complexity of first Fourier transform. We generally use trigonometric symmetries. Then upon the numerical symmetries and remove redundant operations, whatever is not required, remove it. And common subexpression elimination. So, whichever computations could be reduced, you can do all strategies, all kind of modifications and manipulations to reduce the computational complexity. But in other words, that is also called a numerical strength reduction. This algebraic optimization, what you can call, you can say that, sorry, that can be called as algorithmic strength reduction. So reduce the complexity of the algorithm. Once the algorithm you get, there is scope for numerical strength reduction, how the computational efficiency could be improved for the given algorithm. Then once you are having the algorithm, optimized algorithm, you can convert that to a graphical notation. You can represent by a graph. Generally, we have commonly used graph is data flow graph or signal flow graph in for signal processing operations, matrix operations. We use data flow graph, and also we can have control flow graph. The details, I think, of data flow graph, control flow graph, etc., will be covered by another lecture. So here we have the computation at the top, it is reflected and it is graphical representation. This side is your computation, here is the control. For the control y, y less than equal to t, this computation has to happen. As soon as y becomes greater than t, then the computation is stopped. So that control exercise is to be implemented. If we have enough hardware, then what we do, we take a subtractor, one multiplier, and three multipliers, and one adder, and we do this one by one the same as this graph is directly mapped to the data path. So if data path refers to the arithmetic circuits and the communication. So basically, data path is reflecting all those components through which the input data will traverse up to the output, and which could be governed by the control signal generated by the controller or the control path. And here we have a simple control path which is evaluating, which is comparing y with t, and as soon as y becomes greater than t, this computation will not be done. So it has to happen cyclically, repeatedly, and otherwise till we get y greater than t. When y becomes t, then the computation stops, because that desired result will be y is obtained. Okay, so basically what we do, we have the algorithm, we simplify the algorithm and do the graphical representation of the algorithm and map that to the architecture. Here, the mapping is straightforward because we are willing to provide enough number of computing units, enough arithmetic circuits we are able to provide. to facilitate all those operations, computational operations need to be performed. So this is a case of no resource constraint. There is no resource constraint in this case. This is a kind of easy solution. No challenge is there. No scope to make it faster also. This is the maximum speed what could be achieved. And of course, there is scope of some increase of speed that I can tell you a bit later. If we do a kind of pipelining here, if you put a register here after this multiplication and this multiplication, then or after this addition, put a register after this multiplication and after this addition. So you can say one iteration will be happening here in this upper part, and the lower part, the last multiplication will happen in the another section. So two pipeline stages you can say. Last multiplication is one pipeline stage, having one register here at the output of the multiplier and one register at the output of this adder. If you put, you can call it a pipeline circuit. And the upper one is pipeline stage 1, the lower one is pipeline stage 2. In pipeline stage 2, we'll have only one multiplication, which is multiplying F with G and resulting Y. So the computation time basically will be equal to almost like one multiplication time and one addition time. Then briefly, I will tell you the objective of mapping an algorithm to VLSI architecture. Why do we do this one? Basically, we know that algorithm is a sequence of operations or arithmetic or logical operations or data transfer, which need to be performed to complete a computational task. An architecture defines a set of components along with their communications to perform one or more computational tasks. It defines the processors, functional units, memory units, their interconnects, and control. And the objective of mapping algorithm to VLSI architecture is to find, design, an appropriate architecture for the implementation of the algorithm as specified by the application. According to the constraints of the application, the constraint may be cost constraint, the constraint may be speed constraint, or power constraint. Based on that, the architecture should be designed and the algorithm need to be modified and need to have a matching of that. So far as the design constraints are required, often the speed performance is a vital thing. Unless you meet the speed requirement, then the system is not going to work. So speed is what something we must look at to have the functional correctness of the circuit or the dedicated hardware or the architecture of what we intend to design. Then power consumption could be vital, and but the industry will look at very much about the cost. And the cost very often is proportional to the size. More the size of the wafer, more is the cost. And also industry will demand the time to market, because if your product is developed when there is no market, then there is no taker and your product goes to waste. And reusability definitely reduces the cost. Size, if it is less, then reduces the cost. Reusability will be another important issue. So often these are not coherent and mutually conflicting. If you want higher speed, your power consumption will increase, and sometimes your cost will increase because you may have to use more hardware, and that will happen because with increasing speed, increasing power consumption will be there, size also will increase. And when you go for reusability, definitely you have to compromise the speed. Reusability very often we compromise the speed. That is why these constraints and requirements of the system or the application are as driven by the market. These are all conflicting. So you have to find out the right kind of trade-off between these requirements and the constraints, and your architecture should satisfy that, and your algorithm need to be modified accordingly. So can we give break after 5 minutes?
Yes, sir.
Okay. So our key considerations are the processing time. Our processors should be fast enough to process the input sample value as fast as they arrive at. If we cannot process, then where do we keep the input? In signal processing, you have got stream of input, and as the rate at which the inputs arrive at the system, they must be processed. If you do not process, your buffer will be filled and you will not have any time again to do that again. Just like the flow of time, if you do not move with the flow of time, the time will never come. And so for that, we should have enough throughput, that is number of output per second, as required by the system, that must be achieved, and the latency should match the requirement of the real-time application. Latency is the delay caused by the processing. So now suppose your initial input comes and your output suppose is available after time tau, then tau is your latency, and throughput is the number of output per unit time. That is why throughput and latency should match your requirement of the system to process the samples as fast as they arrive at. Then the power consumption, more demanding in portable and embedded systems, but everywhere power consumption is important. Even in IoT applications, machine learning, where 24/7 will be running the systems, their power consumption is very important. Because you have a video surveillance system that is running, your camera input is coming, you have to run 24/7. So you have to minimize the power. And interconnects also reduces the speed, also increases the power. So you need to reduce the number of interconnects. As in FPGA, you'll see the routing delay becomes more than the processing delay very often in different circuits. And IO requirement also should be reduced. Their algorithms should be so designed that you should use minimum number of IO, because your IO pairs take a large area, and IO requirement need to be reduced, and your area cost area, which is also proportionate to the cost, it should be reduced. So, often area could be traded for speed or power, provided the cost allowed. If you are able to make the system costly, some specific applications, like the defense applications, your cost should be could be increased, and area could be higher, and you can achieve higher speed and lower power. There are some definitions I have already told: throughput and latency. And critical path determines your clock period. If critical path is more, your clock period needs to be more. And critical path is the longest delay between two registers. So 5 minutes break will start.
Some important definitions. Throughput is a number of output produced in a given amount of time, usually expressed as number of output produced in one clock cycle. Latency means heat. Latency is the time delay interval of time between the movement of processing in each.
Kumari sir, Kumari sir.
Okay. We'll discuss it after the break.
Sir, you may conclude, sir, because it's already time is 9 p.m. So within 5 minutes, 10 minutes, you may conclude.
Okay, so
Then the
not
question answer session is there.
So as I told, throughput is
Not
the number
required,
of output produced in unit time. Generally, it is unit time. Your unit time may be nanosecond or maybe one clock period. So people express in different way. Generally, number of outputs produced in one clock cycle. And latency is the really initial delay, that is the time required to get the first output. And when we have a big circuit and we have so many sections, so many resistors, so critical path will be the longest time taken in any section between two resistors, or input and the first register, or register and the output. In the circuit, input is there, register, output is there, and the registers in different sections are there. So any path what you find, input, either input to the register or register to output, or between two registers, whichever path is longer, that will be called as the critical path. And the clock period cannot be less than the critical path. If clock period will become less than critical path, then your data will arrive at certain section where the computation is not yet over, cannot take your data. And that will lead to wrong result. So critical path need to be less than the clock period. Clock period should be higher than the critical path, so that the computation will so happen that the correct data will reach at different sections of the circuit. Then how do we map an algorithm to appropriate architecture? There are different mapping methodologies are there. We have, depending on the type of designs and the constraint, we do the kind of mapping. And for that, we should know our design goal. What is our design goal? Whether we need to increase the throughput rate or we need to reduce the clock period. That means we need to run the system in higher frequency. Accordingly, we can design the circuit, or we may intend to reduce the power consumptions, or we may like to reduce the energy per samples or energy per computation. And our goal may be to reduce the overall area as well as the cost, because cost is related to area generated. Very often we go for trade-off, either area delay product or power delay product or energy delay product. So what is the delay in the circuit, computational delay, and what is the area? If you multiply the, because in some circuit area may be more, delay will be less. When area is more, that means cost is more, and you are agreeing to afford more cost, more area, then but you want faster computation. At that time, area delay product is important. And suppose you can run the system slowly, but you do not want to increase the power. So your clock period may be higher, your overall computational delay could be higher, but you want lower power. So in that case, power delay product is important. Similarly, in very rare situation, if somebody is trying to afford more power with less delay, then also it is good. Power delay product can be a kind of metric. And energy delay product, in some cases, people use where much more emphasis is given to the time cycle, time and energy both. Interconnect minimization is another thing also related to the power consumption and the size. And IO also is not a separate thing, but IO minimization will lead to computational bandwidth reduction. That means for IO pin, you have that means every IO pin is utilized for more computation. Like you have X number of computation and you have N number of IO. So number of computations per IO is X over N. So when X over N is larger, at that time you are using less number of IO pins and doing more computation. So that is very good for VLSI design. We'll have less area, less cost. Pins are costly and pins lead to more area. I think we can skip up this one, and this is for real-time processing. Somebody is speaking here, the audio signal converted to digital form, suppose in a communication system, suppose it moves to several embedded processors, and the output side, when it goes to the listener, again digital samples are converted to analog form. Here, as you see, the number of samples that gets into these processors must be equal, and this all those samples will be processed in the same time. So if S number of samples arrive at the processor per second, and N number of computations are performed for every sample of the algorithm, then computational demand per second is N times S, and that must be met for real-time processing. Otherwise, real-time signal processing cannot happen. That is why for video signal, you need very high-speed processors. How to enhance speed performance? Speed performance you can enhance by concurrent processing. One is inherent concurrency, which is parallel processing. The other is derived concurrency or pipelining. So I'll give the example of parallel processing. You have got 5 officers processing a stack of 5 that is at the middle here. At the middle you have a stack of 5, and 5 officers are processing a stack of 5 concurrently. Okay. If one officer can do this work in 50 minutes, then ideally it should take 10 minutes if 5 officers work in parallel. So this becomes a parallel processing. Okay. So here throughput increases 5 times. So 5 times more number of files are processed. Okay. This can be done in some structure like shared memory processors, and 5 processors are there, and from the shared memory get the data and the process. In dedicated architectures also you will have similar thing, but the data is independent, not that file from what one officer will do that has to be used by another officer. So all the files here are independent. If the job is independent, you can have this type of processing. Feasibility of parallel processing. Suppose you have this type of multiplication, 25 times 37, 18 times 29, 34 times 51. Okay, so I have a multiplier which is doing this product. I have another multiplier which is doing this another product, and another multiplier doing this product. So all are independent. All 3 multiplications in this case are independent, and they could be done. So it is done in 3 parallel systems. 3 multipliers are doing 3 parallel systems. If I have only one multiplier, then I will use a control signal. So one multiplier will do this multiplication, then in the next iteration it will do another multiplication, and in the next iteration it will do another multiplication. So in 3 clock cycles, this can be done by one multiplier, but in parallel, by parallel processing, in 1 clock cycle, all the 3 multiplications can be done because they are independent. Suppose in case 2, we have like this, just 10, 25 times 37 plus 18 times 25 plus 34. So how we cannot, here the computation is dependent, the precedence behavior. You cannot multiply 25 here before the just like you cannot add 18 before you multiply 25 with 37. After adding 18, you have to wait for the result and then multiply with 25. After this product is over, then only you can add. So there is a data dependence here, and you cannot do anything parallel. So it has to be done like this. Okay. If the system is like this, if the data dependence doesn't allow parallel processing, you can do pipeline. That will come next. Here by parallel processing, one example I am giving. Here is a one railway track, railway line, and 100 kilometers per hour, you have a small shuttle train. Okay, one bogie train. So one train will reach to the station from station P, from station A in each hour. Okay, 100 kilometers distance is there, speed is 100 kilometers per hour. So in each hour, one train will reach, and if one train can contain 100 passengers go to the one side, to one station, to other station. If you have 2 tracks, you take 2 trains like this, and now 2 trains per hour it can go. Okay, double the number of people can go from station A to station B. If you have got 4 trains like this, and you can run 4 trains in parallel, and 4 times people can go from station A to station B in every hour. So there you require 4 tracks. Pipeline is something different. So what do I do? This distance is 100 kilometers. After 50 kilometers, you put a signal post. Okay. So one train goes and it will wait at the signal post. When the green signal is given, then it will go. At that time, another new train will start. Okay. Then after some time, another train will start like this. So here, in which interval of time a new train will start? 50 kilometers distance, and they are running 100 kilometers per hour. So after every half an hour, you can start a new train, and they can go. So in every half an hour, one train will reach from station A to station B. So without having another railway line, you are able to deliver same number of passengers in half the time in a two-stage pipeline system. So if I will have three signal posts at a distance of 25 kilometers each, then you see what is happening. So here is signal in 25 kilometers. It can go in how much time? 15 minutes. In 15 minutes time, it reached here. So after 15 minutes, a new train will start like this. And then again after 15 minutes, another new train will start. Again after 15 minutes, one new train will start like this. So every 15 minutes, one train will reach from station A to station B. So here the throughput is increased 4 times using only one track. So this is something called pipeline. In dedicated circuits also we can have like this type of things. So 4 trains will reach to station B from station A in every hour. One train in every 15 minutes. In digital circuits also you can do like this. One output in every clock period now we are getting. So to do this computation. So here this is a pipeline register. So parallel out set of D flip-flops. So if your data is 16-bit data, then you will have 16 D flip-flops to have a register like this. Put it here. So once this multiplication, these additions are over, suppose clock pulse goes high, this will go to the other side. At that time, this will reach here, and here you will have a new data. So the result will be passed to the other side, second pipeline stage, and it can take new data. So the time period can be equal to time required for one multiplication and one addition. One multiply accumulation of operation. Okay, so before pipelining, the time was almost equal to 2 multiplication time. Remember that one multiplication time is almost equal to one multiplication followed by addition. Very little extra time required. This is not one multiplication time plus one addition time, but almost equal to one multiplication time. Okay. So by this, after pipelining, your clock period becomes one multiplication accumulation time. So here the time, the clock period is reduced to half, and by this your throughput will increase, will be doubled. So more number of output you will get. In general purpose processors also we will have this kind of thing, but it is done, pipelining is done in different way. In every execution cycle in general purpose processors, we fetch the instructions, then decode the instruction in different clock cycles. And we fetch the operands in another clock cycle and execute the operation using the fetched operands in another clock cycle. We write back in another clock cycle. So in various stages, we execute the instructions, general purpose processor. But here in the dedicated circuits, in dedicated VLSI systems, when we have got several processors, between the processors, we can put the pipeline registers, and our throughput could be enhanced. This is regarding speed. There are also scope how to reduce power consumptions and how to reduce the interconnect. There are different methodologies are there, and perhaps in subsequent lectures, certain more things are planned. A lot of emphasis will be there on approximate computing, that is numerical strength reduction. reducing the complexity of the algorithm, by that reducing the power consumption and increasing the speed of computation. So I hope everything will be going on fine. And we have time, I think 15 minutes. Please feel free to ask any question you like.
Dear participant, you are welcome to ask your doubts.
Yeah.
Any doubt? Also, you can text in the chat box.
Hello, sir.
Yes.
Sir,
Hello?
about seen this.
Hello?
So, like we have, sir, PD power delay and area delay product. What is this PPA?
Power delay product, PDP.
So it's PPA, PPA. So I will write
In this time
in the chat
you
box,
saw
I think.
PDA, then you saw
Sir,
this PDA. I think that is typing mistake. It is power delay product. The slide whether it is PDA written. Which slide number? Can you tell the slide number? Area delay product, power delay product is PDP. PDA is not there. ADP is there. Area delay product is there. Power delay product is there.
No, sir, he is asking about PPA.
PPA, oh, that is same, power, performance and area. PPA refers to what we call power, performance refers to speed. Okay, and A for area. PPA generally is three major design indexes. Here also what we have taken that here speed performance, power consumption, and area. Area relates to
Sorry.
Kamu bela pun siapa? Ah, bapak itu siapa? Eklik kalau biasa coba deh ya.
what we discussed that your area relates to the cost. So size
বহুত দিন পরে ফিল্মটা ফার্স্ট টাইম ইন্ডিয়া
yes here in the design constraint, what we discuss about the speed performance, that is performance,
sir. See,
and power
नहीं
consumption.
से ଗୋଟେ South Indian
Area also relates to the size or cost.
म्यूट କରିଦେଲେ ସେମାନେ ପୁଣି ଥରେ ଅନ୍ୟ କ୍ୱେଶ୍ଚନ ପଚାରିକି
Anything, any other question?
No, sir. There is no other question. Thank you, sir. Thank you very much
Okay.
for giving a very nice talk on and discussing about the basic concept of algorithms and architecture. You also discuss the VLSI design consideration like power, performance, and area, along with the importance of regularity and modularity of the VLSI architecture design. Also, within the discussion, you covered the key concept, methodologies for mapping algorithms for suitable architecture for achieving the desired timing performance, chip area, energy consumptions, and trade-off consideration. Thank you, sir. Thank you for giving us time and deliver nice talk. Thank you very much, sir.
Okay. You're welcome. Thank
Thank
you.
you. Thank you, sir.
Thank you, sir, very much.
Thank you, sir. So today this session is over. So tomorrow there is a session at same time at 7 p.m. So all are requested to join at time.
Thank you, sir.
Thank you, sir.
Okay.
Thank,
Okay.
thank you. Thank you, sir. Thank you.
Thank you, sir.
Okay. Okay. So I'm logging out.
Yes, sir. Yes.
Okay.
Sir, namaskar. Sir, namaskar.
Namaskar. Namaskar.